Hey everybody, how's it going? Stoner Dave here, and my last video I'd said if you asked nicely, I might tell you the schematic and how the circuit works. Well, I honestly didn't expect to get this much of a response, but there's a lot of people out there that seem to like the circuit and like how it works and want to know a little bit about it. So without further delay, let's go ahead and take a look at the schematic. Now, before I pull up the schematic, I want to talk a little bit about it because, like I said in the video, it's kind of a bastardization of the astable oscillator. Now, I did draw out the schematic. Let's see here. Yeah. So this is the schematic for the astable oscillator. Now, before I go over the actual circuit that I built, it's important to kind of know how this circuit operates. Luckily, I was able to put together a little bit of an animation to show the circuit and how it functions. And this program that I found that is able to do this animation, really good program, and makes it really easy to detail the operation. So let's go ahead and take a look at this circuit. It's the astable oscillator, and I'll go ahead and pull that up. Let's take a look at it and talk a little bit about the circuit while it's going. Okay, so this is the astable oscillator. As you can see, we have a power source here. In this case, it's showing a 5-volt power source. We have an LED, a current limiting resistor going into a bipolar junction transistor. In this case, it's an NPN. We have a capacitor that's going from the collector of this transistor to the base of this transistor. We also have a resistor going here to the base of this transistor. We have a resistor going to the base of this transistor and a capacitor going from the collector of this transistor to the base of this transistor, and a current limiting resistor and an LED over here. So what you see here, if there's a way, let me see if I can pause the simulation here. So as you can see here, this transistor is off. There's no light on here. This one is on. Now when this transistor comes on, this capacitor that was charged up to, I believe it goes up to about 4 volts. When this transistor comes on, this collector here goes down to 0 volts. Now this capacitor that was previously charged to about 4 volts, I think it is, or around 200 millivolts, I guess. All of a sudden, this point here that was originally up to about 4 volts drops down to essentially 0. Meaning on this side, we have a negative charge. And you can see it on the graph here. This is the purple voltage. It's coming up here, and let's go ahead and resume. Now what happens is as soon as this transistor turns on, right, its voltage drops down to 0, and the base voltage of the other transistor, represented by this purple line here, drops down to this negative voltage. At which point this LED becomes on. This voltage is negative, so this LED goes off. And this voltage here becomes a high voltage and starts charging this capacitor. Now, once this capacitor gets charged up, what will happen is it'll turn on this transistor. So let me go ahead and resume the animation here, and you'll see that, bam, that comes on, and you see this one turns off. And let me see if I can time this right so we can get it right at the point of turn on. All right, so here we go. This this transistor just turned on. So you can see the collector voltage went from a high to a low, which means that this capacitor, which had, I think it goes up to about somewhere around 20 millivolts, somewhere like that. It's a really low current that goes to the base here to activate it. But what happens is this goes down to a negative voltage. As you can see on the oscilloscope here, the green line represents the base voltage of this transistor. It's at a negative voltage. Where this orange line is the 0 volt line, or just a hair above it. As you can see, what's happening here is that when the transistor turns on, the capacitor that's going to the base of the other transistor ends up with a negative voltage on the negative side of this capacitor. And then this will begin to charge, and once this gets up to charge, it'll turn on the other transistor, and you'll have a kind of a flip-flop oscillation happening. So one will turn on, then the other one will turn on, and it just kind of goes back and forth, back and forth. Now, the only difference between this circuit and the circuit that I have is these resistors right here become connected with a potentiometer that goes up to this voltage supply through a push button. So let me go ahead and pull up that circuit. I don't have a readily available simulation for this. Unfortunately, the subscription for this to be able to add more components to it is not something I'm willing to pay for. Sorry guys, it's nothing against you, it's just I'm not willing to pay that for this option. Sorry, not sorry. But I have a pen and paper, or in this case pencil and paper. I'm more than happy to draw it out. Okay, so here you see the astable oscillator running by itself here. As you can see, no interaction from me. It just keeps running at a constant signal, just like what you saw in the simulation on there. And here you see the circuit that I have, that I showed you in the last video, with the push button there that sets it off and then goes through its little ordeal until it stops. Here's the schematic for the completed circuit the way that I have it drawn. You see here's our voltage source. In the case of my circuit here, it's a 9 volt source, but you can use almost any source really, as long as there's enough voltage to keep it going. I'm finding that about 1.5 to 2 volts is enough, but of course you want to be able to activate the LEDs, so a 3 volt source will be enough to actually make it run. As a matter of fact, I'll go ahead and lower my voltage source down to 3 volts here. As you can see, the oscillator is still running here, and this guy here, although dim, is running. I'll get a little closer, you can see him. Still runs, just like I said, it's a little dim. So the 9 volts will give you the current that you need for a little bit of a brighter light. So the current limiting resistor here and here, you don't really have to worry too much about that, as long as you make sure that your LEDs won't be burnt out by having too much current going through them. For these resistances here, I'm using a 1K for both of them. Put a little omega there. These are red LEDs. Forward voltage is approximately 2 volts for the LEDs. The frequency that they flash at, that's going to be determined by, well, in the case of the astable here, like this one, which doesn't have these resistances here, and this would be connected to VCC directly. For those, it's just the resistance there. For mine, because it does have a split here, this resistance is connected directly to here, whereas these go around here. So I basically add a resistor to go up to the potentiometer, which goes up to the push button, and I have a resistance that goes up here. Again, we don't necessarily need those, but it does make it easier to lay it out on the circuit board. So I went ahead and included that in there. For the setup that I have, we have 47K for all four of these resistances, and this is a 50K pot. The capacitors here are 1 microfarad. And this capacitor here, I believe, is 100 or 10. I can't remember offhand. Let me see. Oh, neither one. It is 47. For that capacitor there. And that's really it. Like I said, when you press down this button, it connects the voltage source to here. So you essentially have this circuit here, just with a bit of a higher resistance there. When you let go of this button, this capacitor begins to discharge. As you can see here, when you press the button, and actually this connection goes to here, not up here. When you press the button, the capacitor is instantaneously charged to 9 volts. It's in parallel with the voltage source. And whenever you have two things in parallel, they become equally charged. So this capacitor becomes charged to 9 volts the instant you push this down, which means when you let go of the button, the capacitor begins discharging. So the way it works is, as the capacitor discharges more and more, we like to think of it as the voltage becoming less and less. But from the eyes of the circuit here, what it's seeing is that the resistance is actually increasing until it gets to an infinite resistance. See, these guys don't really understand voltage on the base here. They look at current. So as the current is increasing or decreasing, they get more and more or less and less action going on. So there is a formula to get the frequency, and that's available anywhere you want to look online. I will tell you that it has something to do with the capacitor getting about 69% of its charge during 1 RC time period. And it takes 5 RC constants to get 100% charged. So that should give you a clue as to how you calculate the total frequency that you're going to get. However, it's not really that important. If you're looking to recreate this circuit, all you got to understand is that you put this push button going into this potentiometer. When you press that down, it goes into the oscillation mode. Now, what's nice is when you let go and the capacitor discharges, which means that it's essentially got no charge there. So when you get no charge here, what happens is, well, let's say this LED is on, this LED is off. So this is essentially 0 volts, and this is about 7 volts. Now, since there's no charge here, this 7 volts is going to take this path here, his quickest path to ground, to activate this LED here. So if you think about this being in parallel, there's not enough current going around to this side to activate this LED. So this one just stays off. And that's all there is to it. That's why when you let go of the button and the capacitor finishes charging, the oscillations stop. It's really that simple. We could put more into it. We could put more thought into it, but that is the plain and simple fact of the matter. You press the button, you get the 9 volts coming through here and through here, making what we got there like let's see, 50, 75K. 9 volts across 75K. That's pretty decent current. Activates the LED, charges the capacitor. Capacitor reached charge, turns on the other LED, which drops the voltage down, turns off this capacitor because this becomes negative voltage on this side, the 0, and the voltage essentially flips, right? So as you see here, there's 7 on this side and essentially 0 on this side. When this turns on, this becomes 0. Well, the capacitor still got the charge. It's just now that this is 0 in reference to ground, this becomes negative in reference to ground. That negative turns this off hard, puts this at the 7 volts, which, since this capacitor is charged, allows this capacitor to start charging through the current that's coming through here. Once he gets up to charge, he'll turn on this transistor, dropping this to 0 voltage again, flipping the voltage on this guy, turning this guy off, and the cycle just keeps going back and forth, back and forth. And that's all there is to it. It's really that simple. So you see why the LEDs turn off and on. You see why there's that delay here when we let go of the button. This capacitor has to discharge through here, which is essentially the same thing as increasing the resistance, right? Until it becomes infinite and no current to charge the capacitors, nothing to allow the capacitors to discharge through. It becomes a stable state. And that's it. That's all there is to it. Everything that you need to know about this circuit to be able to build it and play with it yourself. Again, you can change the resistance values. You don't have to use any particular resistance values in here. It all matter of what frequency you're looking to create. As far as these resistors over here, these are current limiting resistors. So you just need to make sure that you have a proper current to be able to turn on your LEDs without burning them up. It's a current limiting resistance. That's all it is. And that, my friends, is how my favorite circuit works. Well, thank you for watching. You have a great day now.